Hi, welcome back to ME4111. We're looking at tutorial sheet 5, and we're currently on question 3. So just to flick onto the question, we're given a truss pin, which is connected at point O, so that's where our pin is. And we have these 4 truss members that are joined together at that point. And we're asked to determine the magnitude of F1 and F2 for equilibrium. So F1 is this one here, and F2 that one there. We're given the angle here for F2. So I know the direction, don't know the magnitude. So I need that magnitude. And I'm also told theta is 60. So this angle here is 60. So for F1, again, I need to know the magnitude of that. I'm given the angles. So I have the directional information. I'm missing the 2 magnitudes of the forces. Okay, so for this one, we're told that the system is in equilibrium. So my free body diagram is simply a pin point because this is a point mass. And again, you should know why it's a point mass, because lines of action of all those forces, if I take the lines of action, just jot them through there, they all go through point O. Okay. So that is my free body diagram then, is like that. See how good this thing is at drawing. I have the angle of information. So that's what my FBD looks like. So because this is an equilibrium, what this means is that all these forces, when added together, sum to 0. So the handiest way to do this is actually to draw them out to scale. What I've done this slide is try to map it out, because it's a nightmare to do it kind of live. And so I'll explain what I'm doing. We've done this in class before, and it's graphical addition. So what we're doing is we're taking a start point here, and we're starting at one of the forces. So the first force I'm taking is this 5 kilonewton one. Okay, so I know the magnitude and I know the direction. So what I do is I pick a scale. So maybe 1 kilonewton equals 1 centimeter, 1 kilonewton equals 2 centimeters. Bigger is better. And so this here is 5 kilonewton meters long. So this might be, say, 10 centimeters on a sheet of paper, or 5 centimeters, okay, depending on the size of the sheet of paper I'm working with, something that is appropriate. And my angle here is my angle that I have here, my 30 degrees. Okay, and I've drawn kind of the coordinates. You can see them faintly here in this. That helped me draw that off. So I shoot that out to this point here. And now I draw a new coordinate system here that I've indicated, just gone over there with red. And I take the next force that I know, which is the 7 kilonewton one. And again, I have angular information on that, so I can work out that angle that it's coming off on. So easily work out this angle here. So again, this is, if I'm using 1 kilonewton is 1 centimeter, this will be 7 centimeters long, or 14 centimeters long. I'm using the larger scale. And I come down to this point here. So by adding those 2 together graphically, I end up at this location, having started there. Now, what I know about F1 and F2 is that they bring it to equilibrium. So if I add these 2 on together, it comes back to 0. So I'm going to end back where I started. But I don't know the magnitude of these things, but I do know the direction. So what I do is, so from my next force, I take my starting point here, which is where I finished with the previous one, and I shoot a line off in that direction. Okay, so at an angle of 60 degrees, I shoot a line off in that direction. So this angle here will be 60. I know it doesn't look good there, but that's what it will be. So I shoot that off, and I know that the other force will close it off. Okay, and that's an angle of 20 there, or 70 to that. So again, I know it's going to come in here, so that'll be 20, this will be 70. And that angle line of action will shoot all the way back. Okay. Now, where these 2 intersect is the values they must have to bring it back to 0. Okay, because this one, I'm starting at 0, shoots out all the way. This one is the last one we added on here, so it shoots off in that direction. So where these intersect gives me the values of these that bring it to 0. So I just measure off this, and what I have is that it's 1.8 centimeters long if I'm using the same scale, or 3.6 centimeters long if I'm using the longer one that I mentioned. And I measured this one off here, and I got a length of 9.6 centimeters, for example. So 9.6 kilonewtons. Okay, and that's the handiest way. The directions is that way and that way. Okay, so that's the handiest way to do it. And whenever you get 2D force like this is the way I recommend you do it. It's the best way to do it graphically. You can do it in CAD if you want. It's handier to do. I don't have a CAD package on my laptop, so I wasn't able to do it there to show you that. But it's a pretty straightforward thing to do. If you draw the scale big enough, you get a very, very nice answer. Generally, students don't like doing it that way. They prefer doing it the other way, which is the analytical method, which is what I've done here. And again, we have the condition that sum of the forces equals 0. Again, this statement is important because it's telling you what you're doing, and you can start adding forces together randomly, but there needs to be method in your madness, okay? So you have to indicate how your solution is progressing. So I'm summing all the forces vectorially and setting them equal to 0. So I've broken every force into an I hat and J hat. So I got F2 cos 20 I hat plus F2 sin 20 J hat. Again, I'm assigning my directions based on the way it's pointing. F1 cos 60 I hat minus F1 sin 60 J hat. So again, it comes out there and down there. So that's how I get this force here. So plus an X minus an Y. Then I have my other forces. I've broken those into components. This one here, and there, and there. And I'll change color to pinky. We'll go to that one, and that's this one, and this one here. Okay. So then I just pull up the I hat terms, the J hat terms. So this is my I hat, and I'm actually after cutting my thing here. So that equals 0. Okay, so there should be an equal 0. Just wrote that out. You can see there just with the when I was cropping the image, I got it off virtually. So 0. I should on those. So I have two equations, two unknowns. I solve them simultaneously. So you churn through that, you get your answer of 1.79 kilonewtons and 9.58 kilonewtons. Now that takes a bit of work going through. The easiest thing to do is just to draw it up to scale the way we've drawn it here. And that gives you the answer pretty quickly. And it takes care of the direction. So that's the preferred way of doing it. But if you want to, again, you can use this approach. There's just a bit more work in it. But in my experience, students prefer doing this instead of drawing things out on paper. But do whatever is easiest for you. If you're doing it analytically, you need to make sure that your method is clear. So you need to have this statement there. Someone needs to be able to follow what you're doing. And again, if I present it the way I have here, where I cut off the equal sign, equals 0. Without that equal 0, these are just numbers. They don't mean anything. So it needs to equal 0 to make a mathematical sentence. So if you're missing this bit up here and you're missing equal 0 and you just have lines and stuff going down, that's just numbers. It's stream of consciousness stuff. You're going to hemorrhage marks in an exam. Someone has to be able to follow your solution and understand what was going on in your head as you worked through it. So just pay attention to that. Okay, that's that, and we'll drive on and do the next one.